All right. This time we'll be working with division algorithms, and we'll start with the popular restoring division. Now, you might have seen a lot of literature demonstrating different kinds of division algorithms, different procedures and steps, right? And the truth is, once you look at a procedure, you go through it and it is right. That's right? But there are different algorithms because of their different cost in hardware and their yes different implications. So for example, there's a very popular one like this, right? So this is the regular normal division, but this is not what we'll be taking now, right? Where you actually keep a register for your quotient, a register for your divisor, and a register for the remainder. That's so popular for starting the whole process. But as hardware optimization comes, then there is a changes in how these things are done, right? Some use a bit of tricks and other techniques to ensure that we get very cheap hardware for that. So still doing this, there are some terms you should know, right? And one of those terms is divisor. So if I'm dividing 7 by 2, right? The 2 here is my divisor, and the 7 here is my dividend. Now, if I divide 7 by 2, I'll get 3, right? Because 3 2 is 6, and 3 4 is 8, which is bigger. So I'll get 3 remainder 1, right? So the 1 left is the remainder. So that's the start. And the process begins like this, at least for restoring division. It says initialize a register called D with your divisor. And if your divisor is n bit wide, then your dividend should be 2n bit long. Now, usually the value of n is chosen to be a radical of 2, like something which is a multiple of 2. So 2n also be a multiple of 2. We'll see more of that later. Then you have to initialize count with n, right? So it means that the number of steps you go through, if you have n bits, then you have to go through 3 steps to fully do the division. So the first step in division is first you have to shift left your remainder register. Remember, you set your remainder to your dividend, and we'll see why. Then the next is that you have to subtract the higher higher order bits of the remainder. You have to subtract the divisor and put it inside there. We'll see that. Now you come and check if your higher order bit is less than 0. That is if the first bit is 1. If the first bit is not 1, then no, then you set the last bit of the remainder to 1. Then if it is not, if it is yes, then you don't have to set the last bit to 1, right? In fact, you restore. So this is the restoration process, right? But a lot of the algorithm talk, let's get into the raw implementation. So we have a question, right? And this question we're actually trying to do, I think, 0, yeah, this is 30. So 30 divided by 4, right? We're actually trying to do 30 divided by 4, right? And 30 divided by 4, I think it's what, 7 remainder 2, right? 7 times 4 is 28. And 28 minus 30 is 2. So yeah, 7 remainder 2. So the first step we initialize, right? Now remember, 4 is this in binary 0100, and the dividend, the divisor, sorry, is 4, yes. And the dividend is what, 30. And 30 is this in binary. But remember, the algorithm said we should set the remainder register. We should initialize it with what? The we should initialize it with the dividend, right? And that's what we have done here. So you have initialized the remainder register with the dividend. Now remember, when you convert this 30 to binary, I think you get less than 8 bits, but you have to pad the front to make it up to 8 bits. I think that one you've already seen that in the multiplication, so I will not be going through that. And yeah, this step is just the initialization, right? The general step that you almost do in both division and multiplication, so it's simple. Now we move to the next step. The next step is here, right? We are doing the very first thing the algorithm tells us. It says before we start anything, we should shift what? Logical left R, right? So it means that the previous remainder, which was this one, we are coming to shift it left, right? So when you shift this one left, that's what you see. So I think here should be just shift left R, right? That's your comment. Now when you shift it left, that's what you get. And you realize that the next step tells you come and subtract what? The divisor from the higher order bits. What is the higher order bits? The higher order bits is just the very first four bits. So for example, these ones, the very first n bits, right? So for example, this one here is 4 bits. So the higher order bits will be what? The very first 4 bits of here, right? So this 4 bits is the higher order bits. I think I can highlight it. Yes. Now it says come and subtract the divisor from the higher order bits. So this is your divisor 0100. Now come to subtract it from this one, right? And now a very short way is this. If you are doing subtraction, just find the two's complement and add it, right? So the two's complement of this one, the two's complement of this one is what you see here, right? And I will add it to this. Yes, and only add it to the first 4 bits. So it's like 4 bits and 4 bits. 4 bits for the down, 4 bits for the top. And when we add it, we get this one, right? But no, remember this is called restoring division. Restoring the sense that when we get a negative answer, we'll try to retrace our steps. So because we got a negative answer, we'll try to retrace our steps. And retracing our steps means that we have to go back to the original positive answer. How do we do that? Simple. Remember here we subtracted and came to get negative. So we just add the same thing again to give us the positive. So we'll come and add this 0100 to this one. And to give us so that's what you see here. And it will give us this answer. Sorry. To give us this answer. Right. Now you realize that this one here and this one here are the same. Yes, because it's actually supposed to be the same. We subtracted 4, we've come to add 4. Right. So in the net, it's not done anything. Yes, so that's for restoring division. Anytime you get a negative answer from the subtraction process, you have to retrace your step by restoring, and that's the restoring process you have done, right? So, even if you already know that, or the restoring will just send it back to the original value, then you can just write it there. But, I mean, for the sake of procedure. So then the next step is fine. We were not able to divide it in the first step, right? We're not able to get a positive answer in the first step. So in the next step, just like the algorithm say, at the beginning of every step, shift your remainder left once. So as you see, we shift left once. You see, this is not like the multiplication where it is after the cycle where we shift. This one, before we start, we shift. So when we shift this one left once, that's what you see. So I think you can see shift left once. Yes. Now, after we shift left, we'll come and try subtracting again, right? So remember, we are going to subtract 010 from the very first 4 bit of this one. Now, the subtraction is the same as the previous one. Find the two's complement and add. So when you find the two's complement and add, realize that we'll get this. We'll get this one, right? And after the addition, realize that you come and get 001111000. Now, yeah, it might shock you that you got an extra carry of 1, but because the remainder is restricted to 4 bits, right? So we keep this one. So yes, so after the addition, so I think this one is the add. After the addition, we get a positive answer. Now, there is an extra thing if we get a positive answer. When we get a positive answer, we don't restore, no. Rather, we set the last bit to 1, right? So this very last bit, we set it to 1, right? And that is called the R0 bit. So we set it to 1. Then now we are finished with step 2, right? So it's just a basic the restoring division algorithm is basically a bunch of tracks. If your answer is negative, then it means that oh you have to go to the next step. But before you go to the next step, restore it by adding back the one you subtracted. Now when you come to the next step and you subtract and get positive, set the last bits to 1. go to the next step, right? And remember, at the beginning of every step, we have to shift left once. So remember, you see that this one is just the left shift of that one, right? Of the previous remainder. Now, we have to subtract from higher order bits, right? Remember, we are subtracting what 0, 1, 0, right? When we find the twos complement 1, 1, 0, 0, then we add it, and we add it, we get a positive answer again. So since we get a positive answer, we should set what the last bit, which is this one, to 1, right? Then we go to the next step. The next step is the same thing, left shift 1. So when you realize that when you left shift this one, you come and get this, right? And after the left shift process, the next part is subtract. When we subtract, what we get is this one, right? Which is a positive answer. The first bit is 0. So it means that we have to set the last bit towards 1 again. So we set the last bit to 1. And that's what you see. Now remember, we are doing 4 bits. So we have to go through 4 steps, right? So we are now at step 0, right? We started from 4 and are now at 0. So that's all. We have finished the whole division process. And so what is our answer? Well, our answer is simple. The very first 4 bits is our quotient, right? And the next 4 bits is our remainder, right? Now our quotient is 0111. 0111 is 7, and 0010 is 2, right? So we are saying 30 divided by 4 is 7, remainder 2, right? Just like we got at the beginning. So that's all for restoring division, right? Now let's move on to the non-restoring version. So the non-restoring version is just like its counterpart, right? So just like before, we were doing 30 divided by 7. Sorry, I did not write it. So we are doing 30 divided by 7. 30 divided by 4, sorry. Yes, we are doing 30 divided by 4. And the divisor is what? 0, 1, 0, 0. And the they said we should initialize the remainder to what? The dividend, right? So 30 in binary, 8-bit extended will look like this. Yes, and here we are just initializing, right? So that's the initial state. Now the next step is, before you start anything, left shift 1. So here is a what? Just a left shift of this one, right? So when you left shift the remainder at the top, you get this one, right? And now the next step is you are supposed to subtract the divisor from the higher order bit. The higher order bit I explained is what? The very first 4 bits. When you subtract, I mean, this one is just the two's complement of that. So when so you are just adding the two's complement, right? You can view it as that. So you add the two's complement of that, you get what? 1111000, which is what? A negative answer. But here we don't try to restore, right? Now if you had tried to restore, we would have gotten this, right? But because this is non-restoring division, we will not try to restore. No, we'll go directly to the next step. And when we come directly to the next step, um just like usual, we have to left shift our previous remainder. Now instead of coming to subtract, right, this time we'll add, right? So you realize that we use the original thing. We do not use the two's complement because we are adding. So we'll add. And now when we add, this is the answer we get. And now we also add to the higher 4 other bits, right? So we'll add this 1111 to the 0100 and we get this answer, right? Now when we add, we got a positive answer, which is what? Because here 0, right? And I think there'll be an overflow, but I've already explained because it's an 8-bit number. There is no need to worry about that overflow. It will just be it's not being the register again, right? We are only consider the 8 bits. So because it's when we added, we got a positive number. We have to set what? The lower order bit, the last bit, to 1. So you realize that this very last bit of the answer, we set it to 1, right? And that's just the difference between non-restoring and restoring, right? Now we can continue. So the procedure says, next you have to left shift your answer because you have finished with the second step. You are going to the next step. Left shift your answer once, So realize that when we left shift this one, we get this one. Then because now here is a positive number, C 0, what we have to subtract the divisor, right? And when you are subtracting, you add the two's complement, right? So here it is, right? And see, we get another positive answer, right? Now, since we get another positive answer, the rule says we should set the lower order base towards 1. Then we are done. So we go to the next step. The next step is the very last step, actually. So the rule says we should left shift the remainder by 1 at the beginning of every step. Now we have to subtract, right? So subtract, you're adding the two's complement again. And here is what you get. Now you realize that it's still positive, right? So we set what? The last bit to 1. And that's what you see. Just like the previous one, the very first 4 bits is the quotient, and the very last 4 bits is the quotient, the very first 4 bits is the remainder. And that's all for the restoring and non-restoring division. So you realize that with non-restoring, before we add or subtract the divisor, we check if our remainder is positive or negative. But with restoring division, we first subtract before we realize that it is negative. We come back to add, right? And basically that's it. So there is one more question that's here. So it's actually the same thing, right? But here instead of um representing the divisor in just 4 bits, right? I chose to use 8 bits, right? It's actually the same thing. So this time, instead of me worrying myself about finding the higher 4 bits of the remainder and subtracting the divisor from it, I can just directly subtract it from the whole 8 bits because the divisor is also 8 bits, right? Yes, and the process is the same. So this is the beginning, right? My initialization step. And my divisor is 0, 1, 1 and 4 zeros behind it. And my remainder is this one, right? So you realize that the very first step we have to what? Subtract the dividend. Now, when we subtract the dividend, realize that the answer is negative, right? But the next step requires to what? Left shift it. So this is the left shift version of that. Then the next step is because our remainder is still negative, then all we have to do is what? We have to add the divisor again. And adding it give us a what? Negative answer. But this is not restoring. So we go back and we go to the next step and what? Left shift again. And when we left shift again, you realize that it's still negative, right? So we have to what? Add our divisor. When we add our divisor, we get this, which is positive now. So what? We set our last bit to 1. Then we go to the next step where we left shift once again. Yes, and in fact, this is actually the answer, right? In our normal circumstances, we are supposed to how do you call it? Subtract the remainder and see if the division fits, right? But actually, this one is the final answer because here we are just doing 7 divided by 3. You realize I get 2 remainder 1, right? Yes. So this is actually the final answer.